Hey, what's up guys? It's Dr. D-Flo and welcome to part 4 of the large format 3D printer build. We're going to do a lot of printing in this video, but first I need to tie up some loose ends and then install the pellet conveyance unit because this machine needs a constant flow of plastic. And with that, let's get started.
Dr. D-Flo.
In part 3 of this build, I could not wait to fire up the printer, but my impatience led me to skipping over a couple important line items. I've since sorted those out, but here is a quick recap. First, I relocated the emergency stop button to the front of the printer. I machined this aluminum housing to not only hold the button, but also 2 AC indicator lights. The red light is wired parallel to the heater for the extruder, and the green light parallel to the bed heater. The lights will turn on, or more accurately flicker, when their corresponding heater is active. If we pop down to the bed, you will notice that I'm no longer using binder clips. They could not provide enough force to keep the glass from sliding around when removing a print. I machined 6 of these aluminum clamps that have 2 plastic bolts each that can be tightened down for variable clamping forces. On the back of one of the clamps is a cutout to install the thermal fuse. This is a different fuse from what was shown in the previous video, but I had realized too late that I did not have the correct tool for crimping a wire onto the end of that first fuse. Perhaps for obvious reasons, you can't solder a wire to a thermal fuse because that heat would blow it. The new fuse uses common spade connectors, has mounting holes, its face is electrically isolated, and was significantly cheaper than buying the correct crimping tool. While I'm down here, I also wired up the touch probe for setting the distance between the nozzle and the build surface after quad gantry leveling. I machined a magnetic base for the probe. This allows it to be repositioned, and if for some reason the extruder were to run into it, it can move out of the way. For aesthetics and to get a better connection between the base and the frame, I milled these end plates that bolt right on. Definitely get subscribed because when I hit 100,000, I'm gonna print and set sail on a life-size Benchy, and you're not going to want to miss that video. The last couple of changes came in the electrical cabinet. First, I heeded everyone's advice and went for a dual SSR for switching the 220 volt lines to the bed. Next, I upgraded the intake and exhaust fans to Noctua Redux to increase the airflow through the cabinet. I then installed these power meters so that I can track how much energy the printer is consuming. I needed 2. One for the 110 volt circuit and the other for the 220 volt. There's been a lot of interest in how much it costs to run this printer when factoring in both energy and plastic consumption. I'll take some measurements and report back the operating costs towards the end of this video. The last thing on my to-do list was to get the stack light to be red when the printer is hot and green when it is cool. Unlike the AC indicator lights next to the emergency stop button, which illuminate when the heaters are receiving power, the stack light will remain red as long as the printer is hot. This is important because it can take a while for the bed to cool down. Now I know that I have not explained the software side of this build, but one feature of the Duet 3D firmware that I want to draw your attention to is its ability to run custom background processes when it's idle or even printing. In this case, I'm having the Duet check the temperature of the bed and the extruder every 10 seconds. And if either temperature is greater than 40°C, then illuminate the red portion of the LED stack. If not, then illuminate the green portion. This is a relatively simple use of the daemon file, which is what computer scientists call this background program. There's no satanic connection, don't worry. But you could imagine how powerful this feature could be, allowing the Duet to measure and respond to external factors during the printing process. Okay, let's go ahead and change gears. You may have seen my most recent YouTube short where I printed the base for a table. But what I left out of the video was me refilling the funnel every hour or so to keep the extruder from running dry. That was definitely a hassle, which prevents me from tackling longer prints. The funnel method also adds quite a bit of weight to the print head, which is already very heavy. So I need a way to pull pellets from a reservoir that sits to the side of the printer and transport them to the print head when needed. Now perhaps you could store the pellets in a bag above the printer and have gravity feed the pellets to the extruder, but I do not have enough clearance between the top of the printer and the ceiling for that option, and it would be problematic to refill a bag hanging above the printer with 100 kilograms or so of pellets. A better approach is to use a vacuum to suck pellets out of a bin, such as this one, and blow them to the extruder when pellets are needed. I'm going to go ahead and fill up the bin with my pre-dried PLA pellets. Nearly all industrial pellet conveyance systems use a Venturi vacuum system, which relies on compressed air to generate a vacuum. If you're not familiar with this type of system, it may be counterintuitive that a surplus of air could generate a vacuum, but that is the beauty of the Venturi effect. I'll put some links down in the description for an in-depth analysis of this effect, but briefly, when compressed air or liquid passes through a constricted region of a pipe, known as a choke, the pressure decreases as the velocity of this gas or liquid increases. This negative pressure, or vacuum, can be used to draw up another gas, liquid, or in our case, pellets, into the primary flow. The sponsors of this project, Massive Dimension, sent me out their complete pellet conveyance kit. This silver box is where the Venturi effect takes place. Let's take a look inside. The pellets will flow in and out in this direction. The compressed air comes from the bottom, where it runs into this beefy solenoid that opens or closes depending on if pellets are needed at the extruder or not. When the extruder is running low, the solenoid flips open and the air rushes to this commercial line vac component. Here is a diagram of how the air flows through the line vac. These constrictions form high velocity air jets, which as we know form a vacuum according to the Venturi effect. Besides the solenoid, which starts and stops the vacuum, there are no moving parts in this system. Therefore, when we set this pellet conveyance unit up correctly, it should run for a very, very long time. Now, the drawback of this type of vacuum is its inefficiency. A Venturi vacuum consumes about 10 times the power of a mechanical vacuum pump for the same flow rating. This is due to the inefficiency of compressed air. This specific unit requires 50 CFM at 90 psi, which is a massive amount. Fortunately, the unit will only be on every now and then, and I'm hoping to get away with my current setup. Let's take a look at what I have in my garage. After moving my plasma cutting operations to my shop, I've not required much compressed air at my house. I only need air for my power drawbar and mist lubrication system for the mill. So I'm a little concerned if my 2 horsepower compressor will be sufficient. Fortunately, I do have an auxiliary 20-gallon tank, and I'm hoping that the pellet conveyance unit will only need to be on for a very short period of time. The other problem that I face is that I do not have the correct air drying equipment here for the CFM required. In hot and humid Tennessee, there's so much moisture in the air. Take a look at how much water has accumulated in my air compressor tank. And that was just after a day of light use. I dried all my PLA pellets at 60°C for 5 hours. And the last thing I want to do is bring them to a water slide as they take a ride on the pellet conveyance unit. Any amount of moisture will result in inconsistent extrusion. I was originally going to purchase a refrigerated air dryer because air leaving the compressor is very hot and needs to cool down to allow moisture to condense. Passing this air over chilled coils is the best way to remove large amounts of moisture for high CFM applications. However, the units that I could afford had a lot of mixed reviews, and this just seems like a piece of equipment that you get what you pay for. So I went with a much cheaper alternative, a passive radiator system, which is just a sophisticated way of saying I'm going to snake pipe back and forth to allow the air to cool and the moisture to condense before reaching the pellets. Do you hear that? I don't either. That's a pretty good sign. There's no leaks in the system. I actually purchased the aluminum tube and the fittings from a company called Pneumatic Plus. No affiliation with the channel, but I was super excited with how quickly everything went together. No special tools required. You just had to get these fittings finger tight, and that was it. Air goes from the compressor to the tank to this first run of tubing. On this vertical ascent, the air will go up and come back around. Any condensate that comes out of the air will come down this vertical tube into this automatic drain unit. Once it fills up with enough water, a float or some other mechanism will lift up, releasing the water, and it'll be expelled out this blue tube. That's repeated another time, and then another time. From here, the air leaves and it goes to my motor guard filter up here. I've shown the motor guard filter in one of my mill upgrade videos, but if you haven't seen that, It's basically a glorified toilet paper holder. Just kidding, this is not what you would use after going to the bathroom. Instead, it's a sub-micron filter where the air comes in, goes through the filter, and comes out. So my plan right now is to just switch these filters religiously to make sure that there's no moisture or junk left in the air. This is the hose for the pellet conveyance unit. I need to mount that to the frame and then connect the air hose. So I have the suction portion of the tubing feeding pellets from the bottom of the bin. I cut the correct length of tubing needed to be able to supply pellets to the extruder. Now it's time to see if we have enough CFM to suck pellets from here all the way to here. The last thing I want to do is to shoot my eye out with a PLA pellet. So I'm going to throw on some safety glasses and I'm going to flip the switch. Yeah, plenty of CFM. I'm gonna have to clean that up now. I have attached the hose, which will carry the pellets to the extruder, to this 3D printed component. Now this component serves two purposes. The first is to let out the compressed air through a mesh in the top of it, and the second is to shut off the pellet conveyance unit once the pellets reach a certain level. Now, when the pellets fill up to this proximity switch, an electrical signal will be sent to the box, shutting off the solenoid, which turns off the compressed air. No more vacuum. Managing this unwieldy pellet hose was not very easy in my short 8-foot tall ceilings. So, the best solution I could come up with is to use a retractor, which applies a constant amount of force to pull the hose up just to keep it from getting tangled in the linear axes. Lastly, I need to manage the wire for this switch along the hose path. I'll do that in a second, but let's fire up the pellet conveyance unit one more time just to make sure that we can fill up the pellets and that it'll cut off once it reaches a certain height. Perfect. I'll manage this wire and then it'll be ready for printing. I printed the chair overnight and the pellet conveyance was able to keep shuffling pellets to the extruder without any problems. If I zoom in on the bed, you can see that there were no adhesion issues. Let's flip the chair up and test it out. It is incredibly sturdy. I weigh 170 pounds and I didn't feel the chair flex when I sat down. If a nice office chair is a 10 on the comfort scale, then I would probably give this one a 7. Similar comfort level to patio furniture, but before we talk more about the design, let's discuss the printing parameters and operating costs. This was a true vase mode print. One perimeter extrusion line was laid down as it spiraled up in the Z direction. The height of the extrusion was 3 millimeters, and even though I used a 5 millimeter nozzle, through cranking up the extrusion multiplier, I was able to achieve an extrusion width of about 10 millimeters. During some preliminary testing, I determined that this large of an extrusion width was necessary for the chair to be strong enough. Here is a partial print where I used a 5 millimeter extrusion width. It's obvious that this would not make a very good chair. My print speed was 20 millimeters per second, which may sound slow, but the volumetric output was about 1.1 kilograms per hour, or about 2.5 pounds per hour, which is 25% higher than the suggested max output of the extruder listed on Massive Dimensions website. The total print time was 18 hours. The flow rate in print time suggests that the chair weighs quite a bit. I can use this scale to determine its weight. At about 17.85 kilograms or 40 pounds, you don't have to worry about this chair blowing away. Every 1 kilogram of pellets with the 1% colorant costs about $8 at the quantities I'm purchasing it at. That puts the material cost at almost $150, which frankly is both very expensive and cheap depending on what you're comparing this chair to. Compared to an injection molded chair that you would find outside of your convenience store during the summer months, then this is very expensive. But if you look at this as more of a statement piece where the layer lines and hollow inner structure, which are only possible with additive manufacturing, are part of the design language, then it's difficult to put a price on this. I could reduce the material use by going down to an 8 millimeter extrusion width, but I really like how strong the chair is now. The energy costs were more manageable even with the bed being at 70C the entire print. The bed consumed 16.5 kilowatt hours, and all the other electrical components consumed 7.2 kilowatt hours, for a total of 23.7. I pay 10 cents per kilowatt hour in Tennessee, bringing the total power cost for running this machine for 18 hours to a little over $2.30. This would be about $3 to run the printer for 24 hours. Once I enclose the printer, I should trap some of the heat in and see some cost savings, but overall, I'm happy that the cost of running the printer is dominated by the material and not energy, even with the 6,000 watt bed heater. If we pivot back to the design language and uniqueness of the layer by layer process, you may notice some inconsistent coloration in some of the layers. This is because the colorant and melting PLA pellets do not have enough time to mix in the barrel due to the high volumetric flow rate. With low mixing, small variations in the ratio of colorant to PLA pellets will affect the color of the extruded fiber at these extrusion rates. The solution to this would be to slow down how much plastic is being pumped out. A smaller nozzle would also be helpful. The extreme solution will be to buy the MDPH10, a much larger pellet extruder that has a longer screw for increased mixing and melting. I printed 2 iterations of this chair. Here was the first prototype. You will notice the back of the chair is a bit too vertical, and being forced to have this straight of a posture for long sitting periods is uncomfortable, even if it is good for my spine. The other problem with the first chair was that I'm most comfortable when my heels are beneath my knees. However, this is not possible with this straight drop on the front legs of the chair. These problems were fixed with the second version that you saw printed. It has a slight lean backwards, as well as this inward slope to allow my heels to be underneath my knees. Nice. I went ahead and printed a duplicate of the second version so that I could have a full dining set with the table.
I'm gonna grab some wine glasses. I can't reach them. Can you grab those for me?
Yeah, I gotcha.
Maybe you should 3D print me a step stool so I can reach these.
It might be cheaper to buy one, but I'll keep it in mind. So Andy was kidding about the step stool in the previous clip, but honestly, it's not a bad idea. Especially since I'm looking for a more traditional print that has infill and overhangs, is not just a single perimeter layer like the chair was. Now I'm sure that I could have created a step stool similar to the chair, but I went with a blockier design to test those features. It'll be interesting to see if the printer will be able to bridge this 100mm gap at the top of the handle. I queued up the print, let's watch it run. While the step stool looks great, there was a large learning curve for configuring the infill. We don't want the inside of the stool to be 100% dense, or else it's going to weigh too much. The ability to lightweight the interior of parts with a sparse pattern is perhaps one of the best features of extrusion-based 3D printing. For the first printing attempt, I selected a rectilinear infill pattern where every layer of sparse infill is printed perpendicular to the previous one. The problem with this geometry is that when it's not intersecting the previous layer, the infill is unsupported because there's no material directly below it. Here you can see the infill sagging and then forming a high point when it crosses the previous infill line. I went ahead and stopped the print because this improper adhesion between layers will affect the mechanical properties of the stool. The solution to this problem was to use a pattern that closely followed the previous layer and did not self-intersect. The gyroid infill worked brilliantly. However, it did not solve my second issue. I had chosen a sparse 10% infill density because, as I mentioned, I wanted to keep the step stool light, and increasing the infill by 1% adds close to half a pound. However, what I failed to appreciate was how much space there would be between the infill lines. This space was difficult to bridge during the solid layers. You will notice some voids in the top layer because the solid layers sagged when they were unsupported by that infill. These flaws can be fixed through increasing the infill, decreasing the speed at which the solid layer is printed, or increasing the cooling. Fortunately, I had anticipated this problem for printing the top of the handles and had the extruder slow down to 10 millimeters per second, which resulted in surprisingly great bridging quality. Keep in mind that the extruded fiber is 3 millimeters in diameter, and that's a lot of plastic that needs to be cooled. It's becoming more evident to me that the bottleneck for printing complex designs at this scale is going to be cooling rates. I've made a mental note to increase my part cooling airflow by possibly adding more fans or a different geometry here. This printer has been working great. It's perhaps maybe even too great because of how much plastic it's able to push out. A lot of my viewers have expressed their concerns with the environmental side of running a printer this large. Now, these feelings are valid, and I'm trying to reduce my carbon footprint while working on this project, which I believe will ultimately cut down on waste because this printer only lays down the material that is needed. Subtractive manufacturing and even injection molding of plastic parts produces a lot of scrap material that finds its way into landfill and even the ocean. I would like to point out that single-use plastics, which are the main culprits in the environmental crisis we are faced with today, are often made up of layers of different materials and chemicals. This can make it difficult and economically unfeasible to isolate the base plastic during mechanical recycling. This is not the case for the objects that come off the large format 3D printer. My first chair prototype and failed bottom of the stool are 100% PLA. I can cut these prints up into chunks with a reciprocating saw and then grind them down to granules with the Filabot reclaimer. These granules can then be printed again. I'm going to create an in-depth video on this whole process, which is another reason you should hit that subscribe button. Before I end this video, I wanted you to see this one blooper. I typically don't show my fails and problems because on some of these larger projects, mistakes are usually more painful than funny, but what I'm going to show you next, I just had to laugh at to keep myself from banging my head on the wall. After a long day of work, I was hoping I was going to come home to a newly printed chair, but when I walked into the garage, here's what I found. About 70 pounds of pellets spewed across the floor. I caught the incident on camera. Here you can see the pellet tube slips off the extruder head and volleys the entire pin of pellets into the air. Because no pellets are making it into the extruder, the proximity switch keeps the solenoid open. To add insult to injury, my air compressor ran for about an hour and a half trying to keep up with the air consumption of the pellet conveyance unit. There is no overheating sensor on this compressor, so it just ran until it burned itself out. This unfortunate sequence of events was costly and time-consuming. I vacuumed all the pellets up with the help of Andy. We removed all the dirt and usual garage grime to salvage as many pellets as possible. To prevent this from happening in the future, I swapped out the weak plastic clamp that you pinch to hold the tube onto the extruder for plumber's tape. But I also sent Massive Dimension some recommendations on making this extruder reservoir beefier because you really do not want this connection to the hose to fail. I also wired the duet to control switching the conveyance solenoid. If the reservoir on the extruder does not fill after X amount of time, then there's a problem and the duet will close the solenoid valve as well as pause the printer. This should save my new compressor if there's a problem filling in the future. I hope you enjoyed this video. There will be a part 5 as I still need to put the enclosure on and set sail on a giant Benchy at 100,000 subs. So I will definitely catch you guys in the next one.